Hello friends, welcome to Science Team. In the last lecture we were discussing about Galilean transformation and we saw that the length of a rod remains invariant, but we saw that the components of the length, that is the projections of the rod on the three axes, remain invariant. That is this is the rod, this is the coordinate system, and we have a rod whose length is a small rod with length delta L. Then it has three components, delta x and delta y are visible, but delta z is not visible in this diagram. So this is z, this is x, this is y. Now we saw that the different components remain same in the two reference frame. So delta x prime equals delta x, delta y prime equals delta y, and delta z prime equals delta z. So the components remain invariant, but what is the actual quantity which remain invariant in a Galilean transformation? So we have many options here. If we just sum these things, delta x plus delta y plus delta z, then it will also remain same. But is it really the invariant quantity in Galilean transformation? So you know that it cannot be the invariant quantity, because you can make many such quantities like a square of these things or cube. You can make many such forms which seem to be invariant in the Galilean transformation, because the three components are same. So delta x prime cube, delta y prime cube, and delta z prime cube will remain same. So, but this is not the quantity which remains invariant in three-dimensional space. So we will search for what is the quantity which remains invariant in three-dimensional space. So we will see this by observing rotation in three-dimensional space. So Galilean transformation and rotation in three-dimensional space makes something which is called homogeneous Galilean group. We are not going in group theory here, but they make a homogeneous group. So we will start with a rotation in space. So let's see it. So consider a three-dimensional coordinate system. This is x axis, y, and this is your z axis. So there is a point P whose coordinates are x, y, and z. Now we are rotating this coordinate system with z as an axis of rotation. So if you rotate this frame by this z axis, along this z axis, then the x axis will move to some other location. So this is your new x axis, we are calling it x prime, and y axis will be perpendicular to the x axis. So this is your y prime. These will be perpendicular to each other. So initially the coordinate was x, y, and z. So in the new coordinate system, x, y prime and y prime, x prime and y prime, the coordinates, these values should change. Because what do you mean by a coordinate? These are the, if you draw parallel lines to the axis. So if you draw a line parallel to x axis from point P, it will obviously cut the y axis, and this is called the y coordinate. So this length will be equal to y. So we are writing y. Now this length is x. From here to here it is x. So in the new coordinate system, what should be the new coordinates of the same point? So for that you will have to draw parallel lines to the new coordinates. So this is a parallel line to your x prime axis, and this is the parallel line to your y prime axis. So if we somehow calculate this length and this length, then we will obviously know the new coordinates of the P point. So we will calculate it by specifying some angles. So let's assume that we have rotated our coordinate system by some angle theta. Now this point, this is your origin O, connect this point by a line. Let the initial angle was alpha. Initially OP was making an angle alpha with x-axis. So now we can write some trigonometric relations, and that will be in x y plane, in xy z frame, or you call it S frame. We have considered this length to be r. So we have r cos alpha equals x. This is the base and this is your hypotenuse. So base upon hypotenuse would give you the cos alpha. So r cos alpha equals x, and similarly r sin alpha should give you y. Now in x prime, y prime, and the z axis is not changing, but still we will call it a z prime or the S prime frame. So in the new frame, the angle with the new x-axis is this, which is alpha minus theta. This is the angle alpha minus theta. So the components will be given by x prime will be equal to r cos alpha minus theta, and y prime will be equal to r sin alpha minus theta. So in this way, the coordinates of the same point is given as two different is spread by two different values in the two coordinate systems. So now we will expand this term, these two terms. So x prime will be equal to r. So we are writing the formula for cos a minus b. If you remember, the formula for cos a minus b is cos a minus b. This is equal to cos a cos b plus sin a sin b, and the formula for sin a minus b is sin a cos b minus cos a sin b. So we will substitute these values in substitute the values from these formulas. So this will be cos alpha cos theta plus sin alpha sin theta. And now you can see that, or better we expand it, r cos alpha cos theta plus r sin alpha sin theta. Now you have r cos alpha equals x. So replace this r cos alpha by x. So this is x cos theta, and r sin alpha is your y plus y sin theta. So this is our transformed coordinate for x. Similarly, we can find for y. So y prime is equal to, so y prime is given by r sin alpha cos theta minus r cos alpha sin theta. Now you put r sin alpha as y cos theta minus, and r cos alpha as your x. So this is your y prime. So if we write it in a systematic manner, then your x prime equals x cos theta plus y sin theta. Y prime equals, we will write the x term first. So minus x sin theta plus y cos theta. And there is no change in the z axis. Z and z prime are same. So z prime equals z. And the two coordinate system, the time elapsed will be same. So you know that t prime equal to t. Time is an absolute thing in Newtonian mechanics. So if we write these three equations in a matrix form, then it will look like x prime, y prime and z prime. Then obviously you should have a 3 cross 3 matrix and your coordinates of S frame. This is your S frame and this is your S prime frame. So x, y, z. So we have to multiply x by cos theta. So you have to put here a cos theta. You have to multiply y by sin theta. Then put here sin theta. And there is no z. So put here 0. Similarly for y prime, we should put here minus sin theta, here cos theta, and there you can write it here like 0 into z plus 0 into z, and so put here a 0. Similarly for z you have 0, 0 and only 1. So this is the transformation matrix equation for a 3-dimensional system. So you saw that how the coordinates of a point transform in a simple rotation about the z-axis. We can rotate it about any arbitrary axis and the calculation will be somewhat complicated, but the concept will be similar. So we are keeping the things simple. So now let's observe how we can find an invariant quantity in a 3-dimensional rotation. So consider a rod whose length is L. You can also take it delta L or L. So you have a rod of length L. Now the coordinates of the points are x1, y1, z1 and x2, y2 and z2. So what will happen if we rotate this coordinate system about the z-axis? You know that under rotation, the rotation along z-axis, only the x and y coordinates will change and z coordinate will remain same. So these x1, y1 will change and x2, y2 will change as we rotate the coordinates. So we will write a similar matrix for these 2 points, which is P and Q, the ends of the rod. So for the P point, the transformation will be x1 prime, y1 prime, z1 prime equals, you can skip the z, but I am just taking it for a consistency. So it will be cos theta, sin theta, 0 and your old coordinates x1, y1, z1. Then minus sin theta, rotation has been made with an angle theta, rotation by an angle theta, cos theta, 0, 0, 0, 1. And similarly for the Q coordinate, Q point, for point Q, x2 prime, y2 prime and z2 prime. The angle will be same because it doesn't depend on the point, it depends on how you are rotating the coordinate axis. So this is cos theta, sin theta, 0, then minus sin theta, cos theta, 0, 0, 0, 1, and then you have x2, y2 and z2. For my case, I am taking a delta here. So this length is delta L. So if you just subtract these two matrices, then you will get x2 prime minus x1 prime, y2 prime minus y1 prime and z2 prime minus z1 prime. And the same matrix in these two equations, we have the same matrix, so it will be common. So you have cos theta, sin theta, 0, minus sin theta, cos theta, 0, 0, 0, 1, and only the column matrix will be subtracted. So this is x2 minus x1, x2 minus x1, y2 minus y1 and z2 minus z1. We will call this delta x prime, delta y prime and delta z prime. The same matrix, we have to write it here: cos theta, sin theta, 0, sin theta, cos theta, 0 and 0, 0, 1, and then we have delta x, delta y and delta z. So this is delta y, this is delta x, and there is a projection on z axis, that will be delta z, and these projections are changing except your delta z, delta x and delta y will obviously change. Now we will just multiply these two matrices and see what happens. So when you multiply it, you will get delta x prime, delta y prime delta z prime, and this will multiply and only give you cos theta into delta x plus sin theta into delta y, and 0 into delta z will be nothing. Similarly, this will give you minus sin theta into delta x plus cos theta into delta y, and 0 into delta z. Similarly, for the third you will get delta z only. So we have delta x prime equals delta x into cos theta plus delta y into sin theta. Delta y prime equals delta x into minus sin theta plus delta y into cos theta, and delta z prime remains delta z, what we expected, that the z component or the z projection should not change. So now you are seeing that if you just simply add delta x prime, delta y prime and delta z prime, then it will not be equal to delta x, delta y and delta z. So it is different from the Galilean transformation which we have seen earlier, that in Galilean transformation these three quantities on addition give you the same result, but here the results are not same. So it seems that in three-dimensional space the invariant quantity is not just this sum, and it is something different from the sum. So we will check it by a trial. So by giving a trial of squaring the three quantities, we will check whether it gives an invariant quantity or not. So we are just squaring these three terms. So delta x prime squared will give you delta x square cos square theta plus delta y squared sin square theta plus 2 delta x delta y sin theta cos theta. The square of this whole square will give you this quantity. Similarly, delta y prime squared will give you delta x square sin square theta plus delta y square cos square theta plus, and there will be a minus sign here, and there will be a minus sign here. So minus 2 delta x delta y sin theta cos theta, and delta z prime square will be equal to delta z square. Now if we add these three things, then you get delta x prime square plus delta y prime square plus delta z prime square equals these two terms. In these two terms, sin square theta plus cos square theta will give you 1, so it will give you delta x square. Now these two terms will add up and give you delta y square, and these two terms will cancel out. If you add these three equations, then these two terms will cancel out, and only this term will survive. So delta z square. So you notice that this quantity is invariant in case of rotation, and you know that for a cuboid having length, breadth b and height, the length of diagonal d is given by d equals L square plus b square plus h square, or it is given by the under square root of these three quantity. So it's basically similar to that, it is giving you the same quantity. So delta x square plus delta y square plus delta z square is the invariant in case of rotation. So we come on conclusion that in a three-dimensional space, when you assume that the time is elapsing at the same rate everywhere, then you don't worry about time, and you only the only thing which can change are the components of any length. So the invariant quantity must come from a combination of these components, and we saw that this is equal to delta x square plus delta y square and delta z square. So in a three-dimensional system, this is your invariant quantity, and we call it as delta s. So delta s square equals delta x square plus delta y square plus delta z square. You can write it in a simple manner like delta xi square and sigma, where I equals 1 to 3. So it will be delta x1, delta x2 and delta x3. For delta x we are calling delta y as delta x2 and delta z as delta x3. So this will be your invariant quantity in case of rotation. So kindly like our video, share our video and subscribe to the channel, and thanks for watching.